Okay, so today we're going to be doing a couple buffer questions, and I wanted us just to review the definition of a buffer. So, a buffer is an aqueous solution consisting of a mixture of weak acid and its salt, or weak base and its salt. Its pH changes very little when a small amount of strong acid or base is added to it. Thus, it is used to prevent changes in the pH of a solution. And buffers are found in a variety of chemical applications. Example of a buffer solution is found in nature is human blood, which is pH is about 7.4. And you have two types of buffer. You have acidic buffer, where the solution is just the pH is less than 7. And you have an alkaline buffer, where the solution is greater than 7. And today we have a problem, right? And it's asking us if 50 milliliters of 0.0 molarity sodium hydroxide is added to 100 milliliters of 0.05 molarity phosphate buffer at a pH of 7.2, what is the final pH? What are the concentration of HTPO minus 4 and HPO 2 minus in the final solution? And we need to show every step of our calculations. It also gives us the pK values under conditions relevant to this problem are 2.1, 7.2, and 12.8. As you can see here, I wrote down the Hasselbalch equation, which is pH equal pKa plus log over the conjugate base and the weak acid, as you can see here. And when we're solving a problem like this, we have to focus on what is given to us. So what is given to us is the 50 milliliters of 0.01 molarity of sodium hydroxide and 100 milliliters of the 0.5 molarity, the phosphate buffer. And step one, the first thing we're going to do, we're going to start with the initial moles of the buffer. So I want to point out something to you. Oh, I forgot to add the pH. So the pH is 7.2, right? And as you can see, is they give us a pKa, right? And they give us a pH of 7.2, and they give us a pKa of 7.2 as well. So let's just highlight this, right? So this basically means that the pH is equal to the pKa2, right? And the acid is equal to the base, right? And I'm just going to write down the reaction real quick so y'all can see better visually. So it's going to be OH minus plus H2PO 4 minus and HPO 2 minus 4 plus the H2O. And you're probably wondering why I didn't put sodium hydroxide. Why did I just put the OH, right? So the reason why I didn't put the sodium is because the hydroxide is a base, right? And when sodium hydroxide is put in water, it fully dissociates. So it'll be sodium hydroxide reacting with sodium plus hydroxide. So it gives us a hydroxide because it's a strong base and it breaks apart completely in water. And the OH is released is what reacts with the buffer. Sodium is just a spectator ion and it really does nothing for the reaction, right? Remember, OH takes a hydrogen ion to form H2O, right? And because hydroxide take a hydrogen ion, this becomes this goes from this H2PO minus 4 to HPO2 minus 4. Okay? So we're going to start with, like I said, the initial moles of the buffer. So the total buffer that's given to us, don't mind my handwriting, is 0.05 molarity times 10 times 0.100 liters, right? Because, yeah, it's for the 100 milliliters of 0.05 molarity phosphate buffer. And that would be the total buffer, right? And that's going to give us 0.0050 moles. And since the acid and the base is equal to each other, right? The acid is going to be half of this, and the base is going to be the other half of this. So the acid, let's write the acid first. H2PO minus 4. Put in acid. It's equal to 0.0025 moles. Because if we divide this by 2, we're going to get 0.0025 moles. And also the base, minus 4 base, it's going to be the same exact thing. Right? And now we're going to add the strong hydroxide base, right? So I forgot to mention, you need to convert the 100 milliliters to liters and the 50 milliliters to liters. You guys can do that on your own. I'm not going to do it. All right, so it's going to be moles OH minus equal 0.01 times 0.05. It's going to give us 0.050 moles, right? Because the hydroxide converts acid into a base, right? So because it converts acid to a base, right? And you're probably wondering, what's going on when the OH is being added, right? So when the OH is added, it pulls a proton from the acid. And when it pulls this proton from the acid decrease and the base increase. So the acid is losing a hydrogen ion proton, right? And what we would do now, we're just going to put acid here. We're going to subtract the 0.0025 minus the 0.0005 moles, right? Forgot to add it here. Made a little mistake. Let me add another 0. All right. And then the acid is decreasing, the base increase, right? So we're just going to put base right here. And that's going to be 0.0025 minus 0.00050, right? Oh. And then when we subtract the acid from the hydroxide, we're going to get 0.0020 moles. And then when we add the base to the hydroxide, we're going to get 0.0030 moles. Right? And then with that, we can just plug it right in the Henderson-Hasselbalch equation, right? And that's what we're going to do. So we're going to put pH, right, equal 7.2, because remember the pKa it gave us is 7.2, is equal to the pH. Remember that. So 7.2 plus log over 0.0030, right? That's the base. And then we're going to put the acid, 0.0020 moles, right? And how to calculate this, right? So you're just going to put 7.2 plus log over 0.0030 over 0.0020 in your calculator, right? And the answer we're going to get is 7.38. Okay. And this is your answer. And we just solve pH buffers.